after we understood why does it happen, we will talk about the reasons of the rising up, of the balls rising up. We obtained this formula from our literature, and we can see here that the main point of it is that we need rotation around two axes, and what's more important, and what is important also, it must be higher than some critical value. So this means that the condition for the rising up of the balls is the existence of both of the rotations. And this means, and this explains why do we need the rotation around both axes, but let us talk why the rotation around two axes leads to the rising up. So at first, let us explain why the mass. Now let us think about the mass rotation on the rope. When it rotates, it has some constant velocity, and because there is some velocity and it changes its direction, there is some force acting on it. If there is some force, there is some. But what is the nature of that force? The nature of that force is that our string is not perfect, so it deforms, and it deforms and the force that makes the ball on the rope rotate is the elastic force. Now, why we are talking about this? Let us suppose that two balls are spun at the surface with rotation around two axes, and the rotation of this speeds of rotation of this axis around this axis are equal. So we have zero velocity at this point and zero velocity at this point. This means that the instant axis of rotation, which is the axis around which the body rotates at this moment, it is directed like this. So if the body rotates around this axis, the accelerations and so the forces are directed to it. And we can see, we will watch just 2 points, one here and one is symmetrical around to it, around the center. So now let us see at the torus of this force, and we can see that it's obvious that the torus of the arm of this force is much smaller than arm of this force. And this means that the moment of this forces is unbalanced, and this means that the balls rise up because of this moment is unbalanced. And it's our something new, because we are the first people to describe this qualitatively. So now, after the balls rise up, we come to the, after some time after the balls rise up, we come to the stationary motion where the speed is constant. When the speed is constant, there is no slip in the bottom point as we saw on the video. So, and this leads us to the no slip condition, which means that the angular velocities of rotation around both axes are equal. So then we will define the angle. For that we will write the Lagrangian and use the conditions of the stationary motion. We will say that the angle theta doesn't change in time, and the angular velocities of these rotations are equal as we defined from the slide. Then by taking derivative and saying that it's equal to 0, we can obtain the following formula for the angle, and after that we can obtain the final formula. After that we put some values in it, and we obtain the final formula for the delay. We will check this formula experimentally, and you can see here is our plot, here our theoretical lines, and our experimentally observed lines. You can see that the theory matches experiment very well. And now let us talk about other ways of changing this, of measuring this, of proving this theory. So we will just make the balls fall on the surface, and this is just the same as the reduction of the gravity. We obtain the angular velocity, and we can see that the angle that we obtained by this formula is smaller than the real one, and the real one is nearly the maximum value of the formula we can obtain here. So now we talked about the stationary motion. Now let us move to the and now we will understand why is it so important for the balls to stand up. We will, to understand that, we will build a graph of the balls slowing down, and we can see here how the angular velocities depends on the time. you can see two zones here. One is when the ball is standing on the one wall, and the second one is when the two balls lie on the surface, so they have a slight friction between them and the surface. So in the first one, we have a rolling friction, which is much smaller than the sliding friction, and in the second one, we have just sliding friction. So it leads us to the understanding of what is the role of the balls rising up, and the main idea for that is that it changes the type of friction, which is much less than when it's just sliding. So now we will explain the process of speed up. When we blow on the balls, we create a zone of high pressure before them, and this leads to the non-balanced force, which grows and which makes the balls accelerate. But higher the speed, then higher the forces of air resistance. So the higher the forces of air resistance, they increase with the speed, and then when the speed have reached some critical value, they are just constant, and this is the reason why the balls achieve the constant speed. So now let us see how it changes with the radius. If we talk about a small radius, its surface is small and the force action on it is not so big. If you take a big ball, there is a large surface, resistance force that acts on it, so we can make it the following. If we increase the radius, we increase the surface, we increase the surface with the area at which the force acts, and this means that the air resistance force is also increases. It means that if the air resistance force increases, that the maximum achievable speed of rotation decreases. So now we will check this assumption theoretically or experimentally, and you can see here that we see that the higher the diameter, then smaller the maximum achievable speed of the rotation. So now let us talk about the conclusions. First, we described the reasons why do the balls start to rotate around the second axis. Then we took from the bibliography the condition of the ball rising up, and after we obtained that, we qualitatively discussed why the rotation around two axes leads to the rising up of the balls, and we found that the force that makes we found the origin why the balls rise. Then we understood, we determined the angle and checked it experimentally. So then, after we checked it experimentally, we built a graph of how the balls slow down and understood the rising up of the balls is the reason why the sliding friction changes to the rolling friction, and we understood that this is the role of the standing up. Then we talked about the increasing speed of our balls and understood that higher the diameter, then smaller the maximum achievable speed. And after all that, we made the conclusions. So here is the literature used. Thank you for your attention.
Okay, so I have a few questions for you. First, do you believe, how do you define bonded?
How would you define what?
Bonded. They said the balls are bonded. How do you define this?
The balls
Are bonded. How do you define bond?
we just connect them with a special metal glue, and we don't and we see that when they rotate, the distance between doesn't change.
Throughout your investigation, do you believe that the balls are always tangent?
Yes, I do. Balls are always tangent. You mean non-deformed? Just
are they tangent? The two balls that you glue together, are they always tangent to each other? Yes or no?
yes.
Thank you. Second question. You always measure the lifting angle by taking a picture of it and then measure it on the computer, correct?
Yes.
Do you take a picture by hand, or how do you take it?
We use the camera at constant place, and we had the balls on constant place. So we just click on the camera and obtain the. No, we didn't take the photo. We take a video, and after that, analyze.
Third question. Can you briefly explain to me why the motion will finally reach a non-stop condition? Why does it accelerate until?
Because if the point of the if the velocity velocity of the point of contact is not zero, there is a friction force acting on it, and the friction force leads to the decrease of this force. So it decreases the speed of the rotation with high speed.
Okay, turn to page 14 of the slide. Can you explain this a little bit?
So we have.
How you reach the maximum angle?
Excuse me?
So, can you explain this again?
Okay, so we have our box volume, and we see that if we just we took we know the radius, we know the speed of the rotation, so we put it into the formula on the previous slide, and we can see that the value of the cosine that we obtained from the formula is like this, and the actual we obtained from our experiment is like this, and this is the value of the.
Okay. Next question, on page 16. You said that external force is a constant. Can you explain that a little bit? At which conditions is it a constant?
Well, it's not actually. It's not actually a constant.
It's not a constant. Okay. Final question. Did you do experiments about acceleration process?
So we just
quantitative experiments.
No, we did not.
No quantitative experiments of the acceleration process. Thank you.
Okay, thank you very much. You should know. Okay, sorry, time is over. You should stop.
So, hello everyone. Today I'm going to be the opponent of problem number 6, hurricane balls. And now we'll wait 2 minutes for your PPT to be ready. So let's first review the question. It says that 2 balls that are joined together can respond incredibly high distance by first unit by hand and and then flow them through a tube. So we know that the keywords here are, we need to reach a very high frequency, and we have to spin by our hand, and then blowing through a tube in order to accelerate. Next slide. So that's our content. First is a review of the presentation. They first perceived this problem, and they made a lot of presentations of the phenomenon, and we have a good explanation of this phenomenon, observed phenomenon, and then they give some pre-experiments of it, and then they kind of classify this whole process into different stages and explain the stage first in theory and then in experiments. And next we're talking about evaluation of the theory. So first there are some pros. We see a very qualitative theory of how the ball obtains a second angular velocity or the angular velocity on the second axis. And the reporter successfully qualitatively explained why the ball can rise. And he also has a correct calculation of the steady state. For the areas to improve, we see no consideration of a lot of different boundaries. I show one here is the if it is applicable of the non-slip condition. We find that in the steady state, he uses this condition for a lot of times, but we don't know if this is actually satisfying. And also, for example, we don't know how, in what circumstances, when the so-called external perturbation happens, the ball will lift up. Because all balls rotating on a tabletop is constantly subjected to external perturbations. But when the angular velocity is small, we don't see the ball rise. So these boundary conditions, we don't see any considerations here. And going into the experiment, the pros are we have a very clear explanation of the phenomenon, and he also considered free fall case, which is extra. And for the cons, we didn't see any clear explanation of your experiment procedure. We only see the data. So we have a question mark here. And also, I don't know how we actually measure the tilting angle or lifting angle. And we see no quantitative experiment on the acceleration process whatsoever, which is one key point of this problem. We just explained how the balls are accelerating, but we see no experiments at all in this phase. And now we only see two groups of experiment data on the steady state, and we see your theoretical value does not really accord with your experimental value. By the way, you don't give any error analysis. So now I'll give you some advice on this. First, for your theory, you first explain how the second axis of rotation is obtained, and then you tell us how the lift-off condition is obtained. So you can kind of bond these two together, and also by a maybe energy approach of the whole potential energy of the system, whether it can reach a stable equilibrium during such state, which can be better understood by most people. This time's up. I think we might going into our discussion part. So can you turn this into the theory part first? So we'll first, can you show us this PPT? We'll mainly use your PPT. Why this? So our first discussion point is why the balls can actually obtain an angular velocity on the second axis and why it can be lifted up. So first of all, the question says we need to spin the balls by hand. How do you understand this? Why do we need to spin it by hand? Because I noticed that on your experiment you use kind of a machinery to start. Right?
Okay, we in our very clear experiments we use the drill just to make them rotate with no initial angular velocity, and when we have just experiment just to show something like the occurrence of the second axis of rotation or something like this, we spin them by hand, as we can see that the only difference is that if we spin them by drill we know the initial angular velocity, and if we spin them by hand, we
So
don't know.
why do we need to know the initial angular velocity?
Just to control everything.
Because you have recorded the angular velocity over time, correct? So if you can
It's
record it.
caused by our
Okay, so
experimental conditions, because our camera for 1000 photos per second, it could take a video only of 4 seconds.
Okay,
as,
understand. So we'll still focus on our key point. So
Yeah.
can you explain to me why it can obtain a second angular velocity? So because what you just answered to me is that you believe there's no significance of spinning by hand, meaning that I can give any angular velocity of these two balls. Or let me make it clear.
Yeah,
So
just-
the balls are here. During the steady state, you see that they rotate this way and also this way. It has two angular velocity on two different axes, correct? And when you first spin it, you give it only this velocity, right? We call it omega 1. It only has omega 1, correct? And just explain to me how omega 2 is obtained.
Okay, just let us draw the balls from the. This is the front view of the balls. So they they are spun by hand, and they have some initial angular velocity around this
Yes.
axis. So then they need a disturbance on the surface, because the surface is not perfect, and they
Yes,
always
exactly.
yes. So the balls rise up. Yes, this means that
Why do they rise up?
because
For
they met
example,
they met a disturbance on the surface.
So you mean that wherever there is a external perturbation on the tabletop, the ball will lift up. Is that correct?
No, just let me explain. We need a disturbance on the surface to make the balls rotate around the second axis. So we take an absolutely smooth surface and just spin the two balls by hand. We will not see the rotation around the second axis. But if we spin them on the real surface, which we will treat known friction coefficient, we will see that they have the origin of the friction is some disturbances on the surface, like heels and so on.
No.
Yeah,
You don't
that's-
really answer my question. Because if I spin this thing, we have perturbation everywhere, but it didn't lift up. So you tell me under which condition will it lift up? So there's always, it doesn't lift up, right?
Okay, because
When will it lift up? So there's always perturbation.
it will.
Okay, so
I just.
so
I think I just don't get the question.
because of the shortage of time, I
Yes.
think we may explain it easier like this. So first, spinning by hand means that's a very random initial condition, correct? So so that's why I asked you why do you control the initial angular velocity? Because the question says spinning by hand, and to my understanding, spinning by hand means that the initial condition is all very random. So we'll have the rotation on both axes, omega 1 and omega 2.
So
One of them might be very big. for example.
Excuse me. You
Yes.
say that by spinning by hand, we
Yes.
make the rotation around two axes.
Yes.
Okay.
Usually omega 1
We
might
take
be
this
bigger.
bottle. I rotate it by hand. You
No,
can
I
see
mean,
it here.
they are spheres. So when you
It's
when you
just one
actually
rotation.
it doesn't matter. So I say it's
What-
very random. So we can also assume that we only
No.
have omega 1. It doesn't matter. It's a random condition. Okay. So because of the friction on the table, when you have this kind of rotation, to make it simpler, there are a lot of the frictional force can change the direction, and this frictional force will soon make the system obtain a second rotation. So that's why I say that this
I
doesn't
don't-
matter, but which actually matters. So that's how these two angular velocities can kind of.
Just excuse me, but
So that's not. And one way to explain that is that. So I see that you did use a Lagrangian approach. You
yes.
use a Lagrangian approach here.
Yes, I did.
Or let's talk about that first. You show me Lagrangian.
Okay, here it is. So it's just full Lagrangian for not steady state on the first picture, and then we simplify it for the steady state.
Okay, so actually, I think this Lagrangian is also applicable for the process before it, And it's very easy for us to draw the potential energy of the whole system, and we show a curve like this. It should be somewhere like this.
And
When angular velocity
excuse me, please. What is the second axis here?
the second axis is the angle, this angle.
Okay.
This angle here. So at this point, that's the steady state. And when angular velocity is very small, we see that you can easily find out. I can show you the curve because it's my own theory. The balls might rotate on a table, and these rotations on a table might be a stable condition or they might be unstable. If that's an unstable condition, then it will reach. So that the lifting up state is a stable condition. So we'll go into our second question. So you said there's a non-slip condition here, correct?
Yes.
Can you explain to me why the non-slip condition exists in the steady state?
In a steady state, when I say the steady state, I mean the state when the speed doesn't change.
Yes.
Doesn't change a lot. So when we have two balls, they rotate around the vertical axis like this, and they rotate around the horizontal axis like just like this.
Yes.
So if there is a velocity of this point is not zero, then there is a sliding on the surface. So like if we take a bottle and just move it on the table, we need much more force to drag
You
it
just
like
tell me,
here.
why is there a non-slip condition? It
Because-
might be more direct.
Because
What would happen if that's slip? So why do
What
you
will
know
happen?
that during the steady state there is non-slip? So I believe you might need to do an extra experiment to verify this. Because this is a very important assumption of theory. But this, I didn't see any verification, theoretical verification of this. So it is very easy to do so.
from this video we can see that in the steady state.
No, we don't know because the balls are all black. It's total black. So we can only see one
No,
location.
no, we have white dots on
Oh,
this,
no,
on
no.
here, and we can see that when
Oh,
when the balls obtain
Understand. Thank you very much. So going to the acceleration process, can you show any experiment showing the acceleration process? 'Cause, yeah. Do you have any experiment on the acceleration process when you blow on it? How do you accelerate? Are there any characteristics, any interesting thing happening when you actually blow on it?
no, I think there is no nothing interesting. We just blow at them and the speed increases.
Oh, okay. You believe that there is no relation on any variables during the acceleration process when we blow on it?
Excuse me.
So when we use air to blow on it, is there any quantitative relation of parameters? Yeah, I think you might have to, for example, airspeed. And
Okay, we can hide the airspeed, we can hide the angular
are there any
acceleration.
quantitative relationship?
Okay, so as I just said, we can hide the speed of the jet.
Quantitative. Quantitative.
Quantitative, no, we don't.
Oh yes, I think you might do an investigation into this because the problem says investigate the acceleration process as well. For example, you can record the motion. So you have done this. You can know the angular velocity and this versus time, correct? And now you can easily calculate the
Obtain the angular
angular
acceleration.
acceleration, and you can change air velocity. I don't know how we use it, but you can easily measure this, and this relationship might be important as well. Yeah, thank you very much.
Okay.
So to summarize, the reporter gave a basically qualitative description of the process before reaching the steady state of the hurricane balls, and he also gives a quantitative calculation of the steady state. During our discussion, we mainly discussed how we would better explain the lift up of this ball. I advised him using an energy approach, I think if you use this, audience might much better understand why for some angular velocities it will lift up and others may not. And the second important point, I think, is that you should add in a lot of experiments on the acceleration process, because other than the steady state, that's what we care about. We need some quantitative relationships. Thank you very much.
Thank you.
Okay, thank you very much for the wonderful time you heard us. My first question is, how many degrees of
just free coordinates and of the center of mass and the angles like this and.
Okay, opponent, sorry, can you give me your opinion? How many degrees of freedom do we have in the steady state?
The steady state,
Yes.
we have 5.
5
In
degrees.
fact, yes, but we do have some restrictions during the steady state.
So with the restrictions, can you tell me how many it reduces them to?
During steady state, I
Yes.
think there are only 2 or 3.
2 or 3. 2, okay. Can you
Yeah.
bring slide 9, please? And in the meantime, you said that we have rolling without sitting, right?
Yes.
So is there no friction?
Excuse me?
Friction.
What
Do we
friction?
have friction?
We have rolling friction.
We have rolling friction. So you wrote a Lagrangian equation,
Yes.
and we have friction.
No, when we write our Lagrangian equation, we neglect all the dissipating forces like friction or resistance.
If not dissipating forces, is there static friction? Why is it spinning?
We just didn't get the question.
Okay, so you said that it rotates first around its own axis
Yes.
and around the axis that you've drawn there.
Yes.
Which one of these rotations happens first? Can you give me your opinion as well?
The first rotation is around the vertical axis.
And then is that transferred to a rotation around its own axis?
Yes.
Do you agree?
I think they can transfer to each other.
Okay, I agree with you. And because you mentioned you have a condition in slide 9 that I was in slide 8, I think, sorry, 8. Slide 8. Oh yes, this condition. According to this condition, they can transfer to each other, but you said that.
No. They can actually transfer
So
into
you
each
agree
other.
that they can transfer to each other?
Yes, but
Okay, can I ask you a question? What is, which the momentum of inertia you have there? I agree.
I feel
Which one is that?
is the moment of inertia of the two balls rotating around the horizontal axis. Oh, around the.
And is the moment of inertia in the same direction as the angular velocity?
Excuse me.
Sorry. And how do you know that it's, you mentioned how do you know that it's rolling without slipping? What do you think? How does
I think he actually experimentally verified it. He put a dot in this ball and recorded motion.
Yeah,
Each turn we see the dot.
And when the speed is not constant, do we have the non-slip condition during the acceleration?
No.
No. Thank you very much.
Okay, you have to start.
Okay, hi, my name is Meg Arpini from Team Iran, and I'm going to review problem number 6, hurricane balls. So the problem states that we have 2 balls that are connected to each other, and we first spin them by hand, as we've already mentioned, and then we blow onto them using a blower, and we can see that the rotational velocity increases. And yeah, so that's the question. question. And so the reporter started off with an explanation, showed us their experimental setup, their observations. They had a quantitative model, and they explained the conditions for the rising. And then they had, okay, I'll explain this up. And so they explained the reason for the rising, the condition that they had, and then they explained the forces for why there was rising. Then they mentioned the steady state, and they had a Lagrangian equation from which they calculated the rotational angular velocity and the angle, and they compared this with each other and verified it with their experiments, the theory. And so then let's move on to the pros and cons. So the theory explained that there was rolling without sliding, so we can use the Lagrangian equation. They explored the stationary motion when there was no change in the angle, and they mentioned the condition for rising, but there was no explanation as to if it's psi dot that turns into phi dot or if it's phi dot that turns into psi dot. And then they explained the reason for the rising, but again the opponents asked them more clearly about that, and they explained they investigated the effect of the diameter of the ball, but they had only 2 different diameters, and they had a lack in investigation because they had no theoretical analysis for the effect of the velocity of the blower, or experiments for the effect of the blower velocity and surface friction of the surface that they were using. And they had a perspective error, as the opponents mentioned, and they neglected the speeding phase, and they didn't mention the forces that cause the rising, and the difference between the initial rotation, as I mentioned. And so the opponent didn't mention the opponent mentioned the perspective error that I was talking about earlier, and mentioned the reason that they reached the non-slip motion, and they asked about the reason for the rising, and they asked about why there is a non-slip condition, and the quantitative relationship for the blower velocity, which I feel were very important problem. And so the opponent asked, I asked them if there was, I asked them if there was how many degrees of freedom the system had in the steady state. And the reporter replied that there were 5 degrees of freedom. The opponent said 2 degrees of freedom if we consider the constraints. But I believe that in the steady state, because we have 3 different rotational degrees of freedom, if we consider the 2 constraints, that there was only 1 degree of freedom. And they asked about the effect of spinning it with the hand, and and what effect it has if we spin them with a hand instead of with what they used. And they said that the difference is between the initial rotational angle. They asked why there's a non-slip condition, and the reporter replied that they experimentally verified it by placing a point on the 2 balls and checking that the distance it travels is the same for both psi dot and phi dot. And I agree that this experimental verification is enough to show that we have rolling without slipping. And thank you for your attention.
Okay, you have 2 minutes.
Thanks to the opponent and to the reviewer for the analysis of my work, and here you can hear the statement of the protocol. Now let us talk about what we obtained from the discussion. We talked about the reasons why the ball start to rotate around the second axis, and we didn't came to the agreement with the opponent because he says that only friction force is enough. But I think that if we have 2 balls standing on the surface, we have friction force here and friction force here, and the moment is balanced. And this means that when 2 balls touch the surface, they don't start to rotate around the second axis. And the reason of the rotation of the beginning of the rotation of the second axis is the rising on some hills on the surface. Then we talked about the using of the condition of non-slipping, and we agreed that our experimental proof for that is okay in the steady state. And as it was brought by the reviewer, when we have non-steady state, the no-slip condition doesn't work. Also, we talked about the reasons of the rising up, and the reviewer said that I didn't name the force that makes the balls rise. So let me just make it very clear. So the force that makes the balls rotate around the instant axis of rotation here is the elastic force. So it creates a non-balanced torque which makes the balls rise, but and this leads to the increase of the force of the reaction of the surface reaction. So the reason why the balls rise is the reaction is the force of the reaction of the surface, which is transferred to the center of mass by the elastic forces. So thank you for your attention.
Okay, now are there questions?
I have a question for the opponent. You suggested using a potential energy approach to understand this problem.
Yeah.
So why would then we expect the ball to rise? Because when it rises, there is greater gravitational potential energy.
So you have to consider all forms of this energy. It's a how do you explain that? So it's the potential energy of the whole system. You take it as a formula of as a function of angular velocity. You take the whole energy as a function of angular velocity and the angle theta, and you can calculate the effective potential energy, which includes a little part of the energy contributed by the how do you call that? The energy of the motion. So yeah, the effective energy shows that when the angular velocity is very small, then when the two balls all slip or rotate on the tabletop, that's a stable condition. But when you have a large angular velocity, it's not a stable condition for the balls to both rotate on the tabletop anymore, while the steady state, which is calculated, is a stable condition.
Okay.
To the opponent and to the reviewer, maybe to the opponent first. The reporter mentions the quadratic drag as the source of, as the means by which the blowing interacts with the balls. Would you say this is an appropriate approach in this regime?
Which drag can you repeat?
The one that reporter mentioned on his presentation.
I think it's mostly appropriate, but you should also investigate into the influence of pressure difference caused by this blowing.
Do you, what is your opinion?
Can you please repeat what drag was with that?
The reporter on his presentation mentions quadratic drag when considering the force balance on one of the slides. I believe this is at slide 60.
The question is whether the drag, which is considered by the reporter, is appropriate.
Do you think this is appropriate?
I guess I think the drag is correct because the
Okay.
Please go to the slide with the references on it, slide 20. Now, you mentioned that you got some of this from paper. Right?
Excuse me?
You mentioned that some of the relationships you used were from literature. How much of the, how far did that extend? Which paper were you referring to?
From the first one, we obtained the condition of the rising up and the condition and the critical angle of the rotation of the balls.
Okay, so did that include the methodology?
Yes.
Okay, can I ask a question to you? In the case of free fall, to compare your measured angle with the angle from theory or not?
We can see that angle from theory. We can see that here the value of the cosine of theta for the experimental one, and for the theoretical one, and for the experimental one. And we can see that for the experimental one is the theoretical one when we neglect the gravity component.
Okay.
Last question. On this slide, it feels to me very hard to see where the edge of the balls are. How certain are you of this 66.4 degrees? What is the error bar?
Errors of this management is about, I think it's just 0.1 degree, because we took a video frame and we just calculate the angle, and this method is quite adequate.
Sorry, can I mention something about the?
I'm sorry, but time was.
В конце дня будет сегодня.
grades for the opponent now. So it's 5, 6, 6, 5, and 3. And the grades for the reviewer. So it's 7, 5, 6, 6, and 5. So for the quite uniform marks, around 5. So anyone want to comment? Maybe I can start. Or no, start.
Okay, I had my two initiatives. I thought I had an issue with the unclear acknowledgement of the reference. Like you mentioned that you got something from a paper, then I asked about how far that extended, and I thought if you're going to go to that extent and taking a mathematical model, you should probably acknowledge that that's what you've done, rather than because it was presented as if that was all your own work. But just being a bit clear about that. The other one was, which is probably the bigger issue, is just the limited investigation of the relevant parameters, like and explanation of how things were controlled, like how the wind speed was controlled and like how far the nozzle away is and things like that. It was unclear about what had been done and how things were being controlled.
I can add something from my side. I was quite happy with how we tried from the start to try to explain. We have some standard light school mechanics, forces and torques and momenta, like what exactly causes the torque to rise the balls, but how we also mentioned that this idea or this approach is something new. Then you shift to the Lagrange mechanism, just to the result and present it comparing to some few experiments, which might even too few. And I would expect also to pay more attention to the actual blowing the face, because if you just blow to 2 balls and you do not explain how exactly you would blow into them, then you exert equal force into one ball and equal force to the other ball. And if they are rotating, then they are rotating, so the torque would cancel out. So I would expect that you would also.
Sorry, can I say, I should have mentioned what I did like. I did think you had a very good explanation of the phenomenon. The way you explained it was really good. I thought I understood that really clearly.
And also, so my partial bearings was the starting one, then plus Paul for the presentation, but then GP just 0.5 for the discussion, because I felt that you were trying to say good things, but like you were just not so assertive to stop the opponent and let yourself to say what how you try. That's why I also subtracted the points for you. So in case of opponent, we have the range from 3 from the radius up to 6 from Ken.
Well, I felt that the opponent, you understood the physics, but I think the communication was a bit lacking between you and the reporter. Otherwise, you asked some relevant questions, but also what I thought were irrelevant, like the emphasis on using the hand, where he used the mechanical turning device. I thought that was not important.
Yes, so I very much relate to this, define bounded, define hand. This is an absolute plague, especially with like high-end teams, asking about very particular details of phrasing of the problems, and sometimes the semantics take control of the discussion instead of physics, and this is something that I would like to never happen. As for where's this 3 coming from, I feel like we spent 6 minutes on the stage, which is really long, trying to get this kind of gotcha moment with, but the rotating on a horizontal table can be an unstable equilibrium. and like, you should just lead with that. If you maybe ask a question or two to allow the reporter to show you that he knows it as well, but at some point, the only thing that you can maybe achieve by like getting him to admit this is this like feeling of accomplishment, and it doesn't contribute to the discussion. It slows it down. You didn't touch on many topics because of that. So like forcing the reporter to say something you want pretty much never happens, especially with people who are quite good at wriggling out of questions. And especially if there is like a single word explanation, just do it quicker, and then we can hear your opinion about this, like why is this important, how we can expand on this. Similarly, you made your point about this unstable equilibrium, and then you still feel the need to draw like multiple graphs of like, oh, the energy, if it has the lowest point, then it's a stable equilibrium. All right, we get it, okay? That you spent 6 minutes on this already. And what like tipped the scales against you was my jury question about the drag. So I feel like when you were watching this presentation, you were trying to find the aspects of this problem that you know really well, and you can like hammer them down and just like show him that you know it better. And that's not very productive. I feel like this the key aspect of this problem is not like the Lagrangian mechanics of rotating body. We know this like forever, and like eventually when you learn how to write down the Lagrangian, it's all about arithmetic. But the thing that requires some inventive assumptions and some actual physical insight is to some extent explaining qualitatively what is behind this Lagrangian. That was done really nicely actually by the reporter. But the fluid mechanics in here, they're highly non-trivial, and as I'm sorry, forget my name. Yes, as mentioned, just blowing at things doesn't make them rotate, and especially it doesn't make them rotate at really high speeds. So I feel like this, specifically accelerate them by blowing, is the really difficult bit of this problem. Yes, so I feel like the way you conducted the whole discussion and the way you approached gathering information to prepare for this discussion led into the situation where we couldn't touch on the actually really exciting part of this problem. So partial grades are half for questions asked because of this semantics stuff, 2 for opposition speech, 1 for discussion with the reporter, and -1 for jury.
For the review, there was range from 5 to 7, so I can start with my 7. I started previously in 8, so I tried to be consistent with my own grading. So I felt that comparing to the Chinese review, you probably had some these points, but you then focus on some other points. And when comparing the prioritizations of your slides and the points that you really and tried to elaborate on, I felt that there was like these prioritizations. So it was not that good, but I appreciated that you pointed out some. There were some 5s from Kent and Ranus.
Below 1 of them, I guess. So for the plus sides, you're asked about the friction and whether the Lagrangian approach is actually applicable. That was also touched by the opponent, whether this is really the case in the steady state and all that. So verifying the assumptions of all this rotational body dynamics, fine. Okay, that is relevant. In terms of question of degrees of freedom, so first of all, that question is a little bit tricky because this is not really well defined. If you have say you have an orbiting planet, you do Cartesian coordinates, and then both of the coordinates change, but we have like one-dimensional unfold. So okay, 1 but you do polar coordinates and everything is constant, so 0, whoops, okay, this is parameterization dependent, and none of the people who are at the whiteboard used the, I would think of canonical coordinates in this system as the ones attached to the rotating body and aligned with the principal axis of the inertial tensor. But they don't use them, so that is a doubly tricky question, which I can handle if it actually leads to something. But you just asked it, and then you're like, oh, the answer is 5, the answer is 3, the answer is 2, and they were wrong, and I was right. I'm like, okay, why should we care? I don't feel like there is much physics behind this. And the same thing as with the opponent. I'm asking about the acceleration and the interaction with the air, and you didn't even see it on the presentation, so like, that is a problem.
Just quickly, I was down at 5. I thought you had some good questions, like, you know, that you were asking about distributive forces and things like that, but I thought what let you down make 2 things. I thought your time management was a bit off, which meant you kind of, and what you ended up doing was basically just giving us a very short version of what the discussion had been and not really stating your opinions. The only things you stated your opinions on were the questions that you asked. You didn't state your opinions on what they had discussed. And that was what I thought was really missing. And that might just be time management. And yeah, it felt like there was a bit too much in your presentation. You were trying to get through all of that and just missed some of the important bits where you should have told us your thoughts.
Okay. So the second